Hello everyone, so today we are going to discuss about the acetoacetic ester condensation. So first I will discuss the general reaction. Second, I will discuss the mechanism of this reaction. And lastly, we will discuss the practice problems based on this reaction. So first, the general reaction. So in this reaction, the starting material is a ester molecule. And we are converting this ester into a 1,3-dicarbonyl system. Why 1,3? Because at 1 and 3 position we have 2 carbonyl groups. And to bring out this change, to convert ester into 1,3-dicarbonyl system, all we are using is a base. Here we are using sodium ethoxide. So this is what we call the acetoacetic ester condensation. Two molecules of ester are reacting in presence of a base to generate 1,3-dicarbonyl system. Is called acetoacetic ester condensation. Now let's draw the mechanism for this particular reaction. So the reaction is, we have two ester molecules. We have sodium ethoxide and we are generating this 1,3-dicarbonyl system. So we know that sodium ethoxide is a base. It is going to grab the acidic proton present in this ester. So this is my ester molecule. This is my hydrogen. So this base will grab this proton, will generate carbon ion at this position. So we now have a carbon ion sitting at this position. This can also undergo resonance with this carbonyl to generate an enolate. So keep in mind that in acetoacetic ester condensation, we are generating an enolate. So now we have this enolate. Let me redraw. So we have used one of the ester molecule. Now second ester molecule will come. So this oxygen lone pair will form double bond. This double bond will attack at this carbonyl. And through conjugation, this ethoxy group is going to leave. And this is how you can generate the final product. So let me number them. This is 1, 2, 1, 2. This whole group has left now, and now 2 is connected to 3. 3 have this 4, which is having this carbonyl group and this ethoxy group. So this one is 4. So 1, 2, 3, 4 are sitting here as 1, 2, 3, 4, and this is how you can draw the mechanism for this particular reaction. Now let's move forward and try to solve some practice problems. Okay, so the first question is, this is my first ester molecule reacting with another ester molecule in presence of triethylamine. So let's see what product is going to form. So we have this first ester molecule A, second ester molecule B, and a base triethylamine. So now we know two ester molecules in presence of a base. Yes, this is a acetoacetic ester condensation. So this is my triethylamine. It's going to grab the acidic proton. In first ester A, there is no acidic proton present. But in ester B, we do have this acidic proton. So my triethylamine will come will grab this hydrogen, will generate an enolate, and we will have this intermediate. So now the B molecule is used. Now second A molecule will come, the second ester will come. So this oxygen will reform a double bond. This double bond will attack at this carbonyl. Through conjugation, this OMe group is going to leave and the product going to be, so this is 1, this carbon is 2, this carbon is 3, and this carbon is 4. So the product is going to be, from 1 I am starting, 1, 2, 2 is now attached to 3, 3 which has this R group, and attached to 4, 4 has this ester group. So this is the product of this reaction. Now the second question is, so pause the video and try to solve this reaction. So this is my first reagent A, this is my second reagent B in presence of DIPA, which is working as a base, and try to pause the video and try to solve this problem by yourself. Okay, so DIPA is a base. Well, DIPA is nothing but diisopropyl ethyl amine. So we know it is an amine, diisopropyl. So 2 isopropyl group and a ethylamine, so ethyl group. So this is called DIPEA. Now this is a base, it is going to grab the proton. Well, molecule A do not have any acidic proton, but molecule B do have a acidic proton. So this will go, will grab this proton, will generate an enolate. So we are going to form this enolate. Now the A molecule, so this oxygen will reform a double bond. This enolate carbon will attack this A molecule, and through conjugation this whole group is going to leave. So now we have generated product as, so let me number them, 1, 2, 3 and 4. So this is 1, 2, 2 is now attached to 3 having R1, and 3 has gone to 4 which has this carbonyl connected SPH. So this is the main product of this reaction, and the byproduct, this whole group has left, which is nothing but this molecule. This is a triazole moiety. So this is the second problem. Now let's solve the third problem. So this is my first reagent A. This is my second reagent B, and we have this F minus as a reagent. So pause the video and try this reaction by yourself. Okay, so in this reaction we have this acyl chloride as first reagent, this enolate, if you look closely, we have already a enolate as a B, and F minus as some source of reagent. to bring out this reaction. Okay, so let me draw my B once again. So this is my B. So this oxygen is attached to TMS. TMS is nothing but trimethyl silane group. So it has a silyl group attached to 3-methyl. This is what we call TMS group. Okay, now the F minus, let me draw my R1, A molecule as well. Okay, so this F minus has a strong affinity, or you can say silicon has a strong affinity towards fluorine as compared to oxygen. That's why silicon prefers to form bond with fluorine rather than oxygen if fluorine is present. So this F minus will attack at this silicon. Now this is an enolate, right? So this bond will form a double bond here. Okay, and this double bond will attack at this carbonyl. Through conjugation, this Cl group is going to leave, and simply you have generated a product which is nothing but 1, 2, 1, 2, 3, 4. 3 having R1 and R2. R1, R2. So this is my 3, and 4 have a carbonyl group. This is now a carbonyl group attached to R3. So this is the final product for the third reaction. Okay, now the fourth reaction. We have one acid molecule. So this is the first step where we are generating A, and then this A reacts with this molecule in presence of F minus to generate B. So pause the video and try this reaction by yourself and find out what is the structure of A and B. So now let's solve this reaction. So we have a carboxylic acid group, and the reagent for first reaction is a triethylamine, which is a base. So this base will grab this proton, will generate a O minus. So now we have O minus. Now this second reagent will come into picture, where this O minus will attack at this sulfonyl group, and through conjugation with oxygen, this Cl is going to leave. So this O minus attacked this sulfur. Through conjugation with oxygen, this chlorine is going to leave, and you can generate. So now this oxygen is connected to sulfur. Okay, so this is the structure of A molecule. Now let me find out the product for the second step. So the second step reagents are so this is my OTMS. Okay, so this F minus, I have F minus as my second reagent. So this F minus will form a bond with silicon. This enolate will attack at this carbonyl. Through conjugation with this oxygen, this whole group is going to leave. I hope it is clear. Okay, so in first step we have generated A. In second step we have these two reagents. So this is my A, this is my second reagent. So this F minus will form a bond with silicon. This oxygen silicon bond will form double bond here, and this enolate bond will attack at this newly generated A molecule, and this whole group is going to leave. So the final product B will be, okay, so this is my 1, 2, 3, 4. This is my final product. This is 1, 2, 3, 4. Okay, so this is 1. Okay, let me count. 1, 2. 2 is now attached to 3, which has R1 and R3. And 3 is attached to 4, which has this ester molecule. So this is the final product. Okay, so quickly a revision type of study. So we have this molecule acid, triethylamine as a base. This is going to grab this proton. O- will generate, which is going to attack on another reagent, will attack on this sulfur. Chlorine is going to leave, and this is how we forms A. Now these are the two reagents for the second step, where F- will form a bond with silicon. This O silicon bond will form double bond here. This enolate will attack at this carbonyl, and this whole group is going to leave to generate B. So this is my B. Okay, so now the fifth question. Okay, so this is the fifth question. Pause the video and try the mechanism of this reaction. So this is my molecule A, this is my molecule B, in presence of sodium hydride as a base and very mild acidic medium, even water can do to generate this product. So try the mechanism for this reaction. Okay, so the molecule A, NaH working as a base. So this H- from NaH will grab this proton and will generate enolate. Okay. So we have this reaction. Now the molecule B, we have generated the enolate. This is my B. I just flipped it, okay? The exact same structure. Now this O- will form a double bond. This double bond will attack at this double bond. This will migrate here and it will generate O-. Okay? Let me number them. 1, 2, 3, 4, 5, 6. 1, 2, 3 having one R, 4 having R1. Okay, this is my 4. This is my 5th. And this is my 6th. Okay, we see a double bond between 5 and 6, double bond between 5 and 6. Now mild acidic medium is present, so this will reform a double bond and it will be taken by the acidic media. So this will be taken by an acidic media, and this is how you can generate this intermediate. Okay, so 1, 2, 3, 4, 5 and 6. Okay, now once again the sodium hydride H- will come. It will grab the proton from this will generate a carbon ion here. So we have carbon ion here. We have generated a nucleophile. This will attack at this carbonyl. Through conjugation with oxygen, this OET group is going to leave, and now we have formed a 6-membered ring. 1, 2, 3, 4, 5 and 6. Basically you have generated the product. Okay, so this is 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5, 6. So this is the product, and this is the mechanism for this reaction. Okay, so now the 6th problem. So pause the video and try this reaction and find out the product. Okay, before you start, you need to know 2 things. First is that when you have a aldehyde and you have this primary amine, it forms imine. Okay, this architect is called imine. You also need to know when you have a sort of ketone and you have amine, it forms enamine. This is called enamine. This architect is called enamine. So these 2 things you need to know. And also you need to know when you have this 1,3-dicarbonyl type of system, when in presence of sodium hydroxide and heat, you do decarboxylation. You release a carbon from the system in a form of CO2 gas. So all this information will be needed for this 6th reaction. Okay, so the first step, we see base. So this base is going to grab this proton. Okay, excuse me, here we have OAT. Okay, both the side we have OAT group. Okay, so this base is going to grab this proton. Because this is symmetrical, it doesn't matter, it will attack here and OAT group is going to leave. So we have proton here. Methoxy group from sodium methoxide will grab this proton, will generate an enolate. And this enolate will attack at this carbonyl, and through conjugation this OAT group is going to leave. And this is how we generate the product for first step. I am writing this whole group for a time being CO2ET. Okay, now in second step we have this molecule. Okay, now because a carbonyl group is present next to this carbonyl group, becoming more -I effect, this is going to react first with this amine and it will form imine. Okay, So we have this molecule. Basically this NH2 formed imine with this carbonyl, and this carbonyl is particularly more reactive because a more extra CO2 ET group, extra electron withdrawing group, is present next to it, making it more electrophile. Okay, that's why this carbonyl particularly react with this primary amine and forms a imine bond. Okay, now once again we have amine and a carbonyl group. Now this can form a enamine. Okay, here I am forming enamine with this nitrogen. Okay, so this is how we have generated the product for second step. So this is the product for second step. Basically this primary amine react with this more reactive carbonyl group to form imine. Now second amine group react with this carbonyl group to form an enamine, and this is the product for the second step. Now the last step was use of sodium hydroxide in presence of heat. Now this sodium hydroxide is basically converting this ester molecule into acid. Okay, so how it happens? We have this ester group. So this O minus will attack at this carbonyl. Through conjugation, this whole group is going to leave, and this is how it converts this CO2 ET into acid, and the final product for this reaction is this molecule. So we have generated a 5-membered ring. That too, it is substituted from all the sides, and we have a newly generated acid molecule as well. So this is it, and thank you for watching.